Hi, everyone. This is a lecture on inferior and superior planets. And we're going to go ahead and switch to the document camera, and I'll take a look at the page in your workbook. We're looking at page 34A right now. So page 34A, if you look something like this, page 34A. So we have a number of positions. We want to try to learn some words here. We have a planet that is superior to the Earth. What does that mean? Well, it's a planet that is orbiting the sun further away from the Earth than we are from the sun, 1 AU. And so that distance is greater than the Earth. Therefore, it's moving. It's further away from the sun. It's moving at a slower speed as it orbits the sun. And so this is called a superior planet. So what are the superior planets, right? So we'll make a little list. Superior. Superior. Let's see. You can't see that. Superior planets. And they are, actually, why don't I do this? Make a list right here. A list of the superior planets. The superior planets are, let's see, starting from Earth, we're going to go Mars is superior to Earth at a distance of 1.5 AU, right? That's more than one. And then we have Jupiter, which is about 5 AU. Just roughly 5 is about 5.2. And then we have Saturn. And Saturn is just about 9 point something, we'll say about 10 AU. And then we have Uranus with a distance of about 20 AU. And finally, Neptune with a distance of about 30 AU. Okay, remember Earth is 1 AU, right? So those are the superior planets. The other kind of planet down here is an inferior planet. And so you can see that that inferior planet is orbiting on a path that's inside of the Earth orbit. And so we have two planets that are inferior to the Earth, and those are inferior. The inferior planets are Mercury with an orbit of about 0.4 AU, right? We're going to actually see that for ourselves. And then Venus with an orbit of about 0.7 AU. Remember, Earth is 1 AU. 1 AU from the sun. Okay, so inferior or superior is relative to the planet. So we can say compared to the Earth, these are the inferior, closer to the sun planets, and these are the superior, further from the sun. But you could actually discuss, you could describe a planet relative to Jupiter, for example. Which ones are superior to Jupiter? That would be Saturn, Uranus, and Neptune. Which ones are inferior to Jupiter? That would be Mars, Earth, Venus, and Mercury, right? And so on. Okay, so take a look at the first picture. And the idea is that we are on the Earth and we're watching a planet that's orbiting the sun that's further than we are. We have these four special positions, right? Here's one, here's the second, here's the third, here's the fourth. And so this is an important word. We'll start with this one. The word conjunction over here means that the planets are lined up with the sun. And we actually have a special name. I want to introduce a new term to you. Syzygy. Syzygy is an alignment of planets and the sun, right? An alignment, alignment of planets and the moon, maybe, sun, moon in a straight line, right? So when we have a planet lined up with the sun, it is called a conjunction, right? So this picture shows you a conjunction. Now, we can't see that planet when it's at conjunction because it'll be on the opposite side of the orbit from the sun. We won't actually see it. So we don't see these superior planets most of the time. We can only see them when, and this is kind of an interesting thing, when we see quadrature, from quadrature to quadrature. Okay, so what does quadrature mean? If you look at this diagram, you can see that the angle between the planet and the sun is a 90-degree angle. On either side, there's a 90-degree angle, right? So that's a 90-degree I'm not drawing my 90 degrees very well, but that's a 90-degree angle. So what does it mean? If the sun is setting, then the planet is on the in the middle of the sky at quadrature. It's going to be crossing the local meridian as the sun is setting or rising. Sorry, rising or setting. In fact, we can kind of think about what it would be if we look at this diagram. When we look at the Earth, if we drew a little picture of the Earth is rotating in this direction. We're looking down at the North Pole, and the Earth is going around the sun in this direction. So if you look 90 degrees away from the sun, is actually going to be about 6 p.m. when you're facing this direction, or sunset. And so when we have a planet at quadrature, it's 90 degrees away from the sun. It's in the center of the sky as the sun is setting. And at this point down here, at the other quadrature, it's going to be about 6 a.m., right? It's going to be that the sun is rising when this planet is at the middle of the sky. And then we have this other position here, which is across from the sun. Again, this is a syzygy whenever you have an alignment of three things in a row. A planet, Earth, and the sun would be an example of that. This is called opposition. So, when will the planet be exactly at opposition? When it's crossing the middle of the sky at local midnight. So, I'm going to make a little note. It's going to be at this position, it's going to be crossing the local meridian at local midnight. Right? So that's kind of a cool thing. So again, these are planets that are orbiting further from the sun than we are. Now, when we look at these planets, you can only see them in this direction, right? Away from the sun. So if you look at that, what does that mean? We're always going to see most of them lit up. So the superior planets, whenever we see them, they're always going to be either almost lit up or completely lit up, right? So they're going to be gibbous, which you know that means. It means more than halfway lit up, but actually nearly lit up or full, right? The superior planets can only really be gibbous or full because when we look at them, we're always looking away from the sun. Okay, they're going to be looking away from the sun. So it's always going to be nearly full. Okay, so that's all I want to really talk about right now about superior planets, but I will probably talk a little bit more in the future. But I do want to focus today on inferior planets. So this is kind of a pretty cool thing. We're going to be able to watch Mercury go through a complete cycle. And when it does, we're going to have a chance to see this beautiful pattern that occurs. And so that's actually what we're going to want to work on today. But anyways, let's talk about that inferior planet, right? Again, there's two inferior planets, that's Mercury and Venus. And you'll see that there's these special positions. We have conjunction, but I want you to notice there's two different versions. So conjunction means lined up with the sun. But if you're inferior to the Earth, there's actually two ways to be lined up with the sun. So one is called an inferior conjunction. That would be the Earth and the planet and the sun. And if you go over to the far side, it's going to be Earth, Sun, Planet, right? That's also a conjunction. It's called the superior conjunction. So if you look at this, I want you to try to imagine. Remember that the half of the planet that's facing the sun is going to be bright, right? It's going to be lit up. So when we're looking at this one, can you tell me what phase it is? I hope you can see that it's just like when we look at the moon, right? When the moon is between the sun and the earth. So all of these, if you look carefully, are going to have phases just like the moon has. And the thing that's kind of cool about the inferior planets is that we see all the phases, right? So this is only possible because they're orbiting closer to the sun. They have all the phases. So they have all the phases. And if we look carefully, you can identify which is which, right? So at the inferior conjunction, what phase would it be? That's going to be the new phase, right? Because we can't see anything lit up. It's all the lit up side is facing away from us. But in the superior conjunction, you can see by the same reasoning, this is when the planet's full. right? So both Mercury and Venus will go through the entire cycle in a slightly different way because they're not orbiting the Earth, they're orbiting the sun, but they are going to exhibit all of the phases, just like the moon does, which is kind of cool. Now, one thing we're going to be asking ourselves, you can ask yourself right now, is when will we see the brightest Venus or the brightest Mercury? And you might be tempted to think that it's when it's full, but that's not actually the right answer. I'll wait a few minutes to share with you why that might be. But it's actually when it's a much smaller moon that it turns out a crescent. It's actually going to be much brighter. And you can think about why that would be. Okay, so when we see the planet, we always can see that it's going to be either going to be lined up with the sun or it's going to be on one side or the other. So if you want to understand this, you have to turn your diagram and use your eyeball. Here's your eyeball, right? You're going to look exactly in this direction. And if the sun is directly over in the middle of the sky, right? Then where is this? Well, this is to the east of the sun, right? The sun goes in an arc through the sky, and when it's in the southern part of the sky, it's in the middle of the sky. But the planet Mercury or Venus right here, when it's on this side, it's east of the sun. We call it an eastern elongation. Now, this is a special one called the greatest. We'll get to that in a second. But if you look at the planet here, you can see that it's actually to the right of the sun or to the west of the sun, and that's called a western elongation. So as you watch Mercury or Venus go around the sun, they're going to switch places, right? So this is western elongation, and then we have conjunction, superior conjunction, and then we have eastern elongation this whole time, and then we have inferior conjunction, and then back and forth. And there's an interesting thing you want to think about. If Mercury is to the east of the sun, then when the sun rises, we can't see it at all. It's not up yet. And in fact, rises after the sun. So make a little note, this rises after the sun because it's to the east. It's eastern elongation. And so that's an interesting thing. So when would we see this planet? At what time of the day? Well, the answer is right after the sun sets. And so when we see Venus or Mercury in the sky right after the sun sets, we call this, when it's on the side, an evening star. This is an evening star because it's eastern elongation, right? The eastern elongation. Elongation is measured as an angle, right, away from the sun. So you can have 0 degrees. Elongation means it's lined up with the sun. And then we have 1, 2, 3, 4, 5. There's going to be some degrees away from the sun. That's called the elongation. And so if you look down here at the western elongation, something interesting, right? This one is west of the sun, which means it rises first. And so this one is going to be in the sky before the sun rises. And so we call it, when it's western elongation, the western elongation is known as a morning star. So both Venus and Mercury can be seen in either the evening or the morning if they are at some elongation. If they're at conjunction, we're not going to see them because they're lined up with the sun. It won't really be visible. It'll be, and when they're close to the sun even, right? So anytime they're really close to the sun, we're not going to see it. So as Mercury and Venus go around the sun, you might think that the place where they are furthest away from the sun would be right here. You might think that, right? Because that makes a right angle. But it turns out if you draw a line to that point from the Earth, you realize that that's not really the best place. The place that is furthest away from the sun, or furthest angle away from the sun, is this point right here. So this is a special point. It turns out that the line drawn from the Earth to the planet, to the orbit of the planet, is actually creating a special line. And when we put that planet right there, this is called a tangent line. So remember, a tangent line touches the circle in just one spot. And so drawing the tangent line, that makes it as far away from the sun as possible. And so that's called the greatest eastern elongation. And what does it mean? It means that it's going to stay in the sky after the sun has set for the longest amount of time. So ancient people would have easily noticed this. This is something that you could just kind of pay attention to. The longer that Venus or Mercury stays in the sky, the greater the elongation. And similarly, in the morning, when it's greatest elongation, what we have is the planet would be up early, the earliest time before the sunrise. Okay, so that's kind of a cool thing, right? So this is the direction that the planets are going around the sun. I haven't shown you that, but this is kind of what they're supposed to be doing. All right. So let's take a moment right now and let's take a look at Mercury and Venus. And we're just going to watch just some cycles. I'm going to bring up the stellarium for us right now. And here's stellarium. And you can play with this yourself. It's actually really a cool program. And I've turned on a few things right now. I've turned on, I did want to go to today's date. So let me go back to today's date. Here's the 15th. I've turned off the atmosphere so you guys can see during the daytime. And I've did a search for Mercury. Oh, I did a couple more things. I turned on the constellation lines and labels. And then under here, I went into star lore and I showed the boundaries to the constellations. I want to be able to do that. And so if you look right here, we've got today, Mercury is in the constellation of Pisces. And we're going to go ahead and highlight the sun, and I'm going to press space to put it right in the middle. And I've got it roughly at noon. Now, there's one more thing I could add. Let's go ahead and put the local meridian, the meridian right now, just to have that. And that, remember, is the middle of the sky. So you can see I've got the sun right on the local meridian. That's cool. It's noon. That's good. This is actually, I just realized it's not recording daylight savings. So that's why it's noon. It should be 1 p.m. But anyways, okay. So back to the story. So you can see Mercury is just a little tiny thing. If I highlight it, you can see I've turned on just a little bit of information. The elongation is 6 degrees, which is interesting. So if you go back just a couple days, that's what I want you to notice. A couple days ago, elongation was actually just 2 degrees, and then about, yeah, there it goes. That was about as close as you can get. And then you can see it was basically not illuminated. It was I could try to zoom in, but I don't know. Oh, I can't see. Hold on. Let me just space it again. Let me try to space that. If I zoom in, you can't really see. Yeah, you can't see anything. It's new. Okay, so that didn't help. Let's center on the sun again. Okay, now watch Mercury. So as we step forward in time, actually, you know what I'm going to do? One more thing. I want you to see this. This is actually kind of cool. Let's turn on the ecliptic. The ecliptic, remember, is the path that the sun takes. So Mercury and Venus and the other planets will always be close to this ecliptic, it turns out. Let's go ahead and watch Mercury now as I step forward in time. So you can see it's getting further away from the sun and further away from the sun. And so this is Western elongation. So today, if I were to ask you this question, what's the elongation of Mercury today? The answer is it is Western elongation. And so it keeps going and it's getting, let me see, I do want to see it actually. Let me go ahead and turn that on. Let's see. You can see it's 2.8%, right? Illuminated, getting 4%, 5%. It's getting further and further away from the sun. 9.8, 11.5. You can see it's getting brighter. It would actually be kind of cool to see. Well, you can see from the diagram that it's definitely getting brighter. And interesting. Okay. And so now it's 33% illuminated. It's actually it's just about at its brightest. No, never mind. Okay. So what's going on, right? As you go further away, it's getting further. So I didn't get to the point. Let me see if I can get to the point. The elongation, let's take a look at the elongation. 26 degrees. And that looks like it's about as big as it's going to get, 26 degrees. So 26 degrees right there, right about there is the greatest eastern elongation. So if I zoom in, you can actually see that it's just a little bit less than halfway lit up. So I said crescent, but I actually just a little bit under halfway lit up. Okay, so I would say it's waxing, but it actually looks like a waning moon phase, right? So it's a little bit different because it's going around the sun. So it's actually really bright right now. So that's about the brightest it gets at that greatest eastern elongation. If we keep watching it, we're going to see something interesting, right? If you keep going, it's going to go back towards the sun. And as it crosses behind the sun, you can see the illumination percent. As it goes behind the sun, that's going to be superior conjunction. There it is, 99.9% illuminated. Superior conjunction. We can't see it because it's too close to the sun. And now, as it emerges, it's now going to be the eastern elongation, not the western elongation. So we're going to see it go further and further away from the sun. Watch the elongation numbers go up, 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 up. And it gets to 22, 23, 24, 25, 26, and that's 20, almost 27, just a little bit under 27 degrees, and then it starts to come back. So that would be the greatest eastern elongation. And as it comes back, we can see it's getting less and less lit up. And it's actually now it's starting to dim. But there's a point in between when it is actually brightest. I probably could have put the magnitude up for you. In fact, let me just do that right now because um, why not? Let's put the magnitude, apparent magnitude. Where is apparent magnitude? Magnitude. Uh-oh. Oh, visual magnitude. Okay, that's what it says. Apparent visual magnitude. Okay, so the visual magnitude is 1.44. Let's back it up. 1 point, yeah, it's getting lower, right? Lower means brighter. 1.09, 0.92, 0.80, 0.64. Oh, it's getting small. Okay, it's getting bigger. 0.4, 0.4, point negative. Ooh, there you go. Negative point. Oh my gosh, it's super bright. But actually, you know what? We can't see that. Interesting. Okay, now I'm a little confused. Okay, so that's interesting. We can't see it when it's that close to the sun, though. So now I am, it looks like the visual magnitude is now going to get dimmer, right, as it gets closer to the sun again. So right here, we're about at inferior conjunction, right about here. Okay, right around here. Okay, so we have inferior conjunction between the sun and the earth. It's a new phase. We don't see anything illuminated. It says 1%, but that's pretty small. Okay, so we are going to do a very cool little activity right now. Now that you've seen the basic terminology, let's talk a little bit about what we see actually with actually, you know what? Before I do that, back to our superior planet. I want to talk to you just for a moment about something that you probably remember, is that sometimes when we watch the planets, they have a normal way of moving, and that normal way of moving is towards the east through the constellations. But every once in a while, they appear to go backwards. Okay, so the normal motion, if you watch us, we're going to do a superior planet, but actually it's true for any of them. A superior planet, the normal motion night after night, normal motion is called prograde motion, and it's to the east, to the east. Okay. But what happens is every once in a while, it will appear to go backwards, right? So it goes backwards, but that's actually not quite happening. It's called retrograde motion, which means it's going to stop and then go back towards the west in the constellations, and that's to the west, right? West, and then it'll go back to normal. It'll be prograde again. Okay, why is that happening? Well, the answer is actually it's just called relative velocity. So if you look at two planets that are orbiting the sun, one of the planets is going to be closer to the sun than, and one is going to be further from the sun. So it turns out that the closer planet orbits faster. This is something we learned, right? The closer you are to the sun, the faster you orbit. So to put the sun in the middle, let's go ahead and put the Earth right here, and then maybe like Mars right here, Mars, right? Okay, I forgot the symbol for Mars. But anyway, so we have right here, this is a This is called opposition, when Mars is at opposition. And if we watch, right, Mars and Earth do not have the same speeds. So Earth is faster in its orbit than Mars is. So it turns out that when we are passing Mars in orbit, when it's at opposition, is actually when we see Mars go retrograde. In fact, that's what's going on, right? As we're passing Mars, it looks as though Mars is going backwards. It's not really going backwards at all. So let's take a moment and look at Mars now. And I'm going to go back to our current date and try to find that for you. So let's go ahead and find Mars. Okay, here's Mars. And what I want to do is I want to put Mars in the middle of the sky. So I'm going to back it up just a bit, just so you can see how that works. Okay, so there we go. It's just about the middle of the sky. Now I want to watch what happens to Mars if I go one day forward. And you can notice that everything's moving forward, but right now it's in Aquarius. But what happens in the next couple days? It's going to move towards Pisces, right? Along, look at the ecliptic, right? It's going to follow the ecliptic and it's going to move towards the east. You can see it's changing its number along the ecliptic. It's moving eastward relative to the constellations, eastward, 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 eastward. And so a couple of years ago, we tracked that it turned around in Pisces, but this time it's going to be a little bit different. So I'm going to let Mars keep going for a while. We might have to adjust it just a little bit to keep it towards the middle of the sky. I want you to see that eastward note movement, right? Eastward, 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 eastward. Okay, there it goes, inexorably eastward, right? Look at this, eastward, eastward. This is just the thing that it does, eastward through the constellations, eastward through the constellations. And so it's just, this is the normal prograde motion, right? It's going to be eastward, eastward. Okay, so it just, this is kind of boring, but this is what it does. So prograde, 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 prograde. And then you'll see something interesting coming up, right? So as we keep going, something happens when it enters Cancer, right? So watch what happens. So in Cancer now, you can see that it stopped moving east, right? So look at what happened in Cancer. Now it's staying in Cancer. And now if you watch carefully, it's actually going backwards towards Gemini, right? So this is the period, if we go back just a little bit, this is actually when Mars begins to go retrograde, right around here. It doesn't get any further than that. So it doesn't get any further than this. This is the moment. And in December, it looks like this year, it's going to start to go retrograde. So Mars will go retrograde, which means it's going to head towards the west now. And I have to shift the time a little bit, but you can see now it's going into Gemini. Let's see how far it goes. Doesn't go very far, probably. Let's just see. It goes into Gemini, and how much further? Oh, it doesn't look like it's going to go any further. So you can see it just went over from here to here. And then if you watch carefully, now it's going to go back to being, now it's going east again, right? So you can watch carefully. Now it's going to go east. It's going to go back towards Cancer. All right, now it's going prograde again, right? So that period is like 4 months, 5 months, something like that, is when it begins to go retrograde. Okay, so retrograde happens because a faster planet is passing a slower planet. That's about it. Okay, all right. So let's see. Oops, I just realized I didn't show you any of that. Let's go look at Stellarium again. Try it again. Let's go back to our current day, and I will try again to show you what I just said I was showing you, and I didn't show you because I forgot to share screen. Okay, 4:15. Okay, here we go. Sorry about that, everybody. Okay, put it in the middle of the sky. Watch Mars. Okay, and it's going to go towards the east, right? So we're going to go watch it. There it goes. East, 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 east. I'm going to change the time just a little bit. East, east, east. So we actually know what's going to happen. It's going to go all the way to Cancer. So if you just keep watching that, you're going to see it go all the way to Cancer. Here it comes, Gemini. Okay. Gemini, almost. Okay, Taurus, then Gemini. Okay, here we go. and we're going to get all the way to Cancer, and then it's going to, so it's going to be sometime in December, I think we said, right? When it starts to go retrograde. So here we go. Okay. And so right around then is when it starts to go retrograde. And then what's interesting is right in the middle of that retrograde motion, I want to show you something kind of cool. At the middle of the retrograde motion, there it goes back. Okay, now it's going westward through Gemini. In the middle of that, you'll notice that what happens is actually Mars is going to be crossing the local meridian right at midnight. And so this, you might remember, has a name. When it's crossing at local midnight, we call it opposition, right? So at opposition is the middle of that period of retrograde motion. It'll keep going for a couple, month more, and then you'll notice that it finally stops going backwards, stop going west, and then it'll come back towards the east again. And there it goes. Okay, so it's headed back towards the east. So it's now doing prograde motion again. Okay. And so now it's going back into Cancer, et cetera. And it'll continue on its cycle. So this takes a long time, by the way. So that's interesting. All right. Anyways, okay. So now we're going to do a little activity in your workbook. And this is actually on page 33A. So everybody turn to page 33A. Right here, 33A. So we're going to we're going to watch which planet. Well, one of the inferior planets, and it turns out the one that's easier, we're going to do Mercury, because Mercury doesn't take as long to go once. It's going to be the shortest amount of time, right, to go one orbit of the sun. So what does the word synodic period mean, right? What does that mean? If you remember, synodic, I'll go ahead and define it right here. Synodic means relative to the sun, right? So what we're going to be doing is we're going to watch Mercury go through one cycle. Actually, we're going to watch a few cycles, it turns out, but we're going to try to catch the time it takes to line up with the sun. So for example, we could use the inferior or the superior conjunction. In fact, we're going to go ahead and use inferior conjunction to the next inferior conjunction. So we're going to go between it. We might do a couple, or a few. Maybe we'll do three. All right. Maybe we'll do three. Okay. So we're going to measure the time, and then using that time from one inferior conjunction to the next one, we're going to watch it. We're going to watch it a few times. That's going to be called the synodic period, right? The synodic period relative to the sun. But somehow we are then going to come up with the sidereal period. The sidereal period means relative to the stars. So, for example, if we ask the question, what is the sidereal period of the Earth? The sidereal orbital period of the Earth, the answer is 1 year, right? 1 year, about 365 days. Okay, so that is called sidereal, right? The time it takes for one orbit of the sun. So sidereal means relative to the stars, relative to the stars, to the stars. And so it's going to mean the time it takes to make one orbit of the sun, right? So basically that's what it is, the time for one orbit of the sun. Okay, so we're going to watch Mercury. We're going to watch it for a year. How about that? We're going to watch it for like a year. And then we're going to see, I'm going to write down some dates for us as we go through this. And so we're going to start with our first, we're going to do inferior conjunction, which happened just a few days ago, by the way. So that's kind of cool. That's actually pretty easy. And then we're gonna keep track of that and then calculate the amount of time it takes for inferior conjunction. That will be our sidereal as a synodic period. But from that, we're going to somehow figure out the sidereal period. So we're back to stellarium. Here we go, back to stellarium. We'll go back to today's date, and it's the 15th. Actually, we want to try to go to Mercury. Let me go ahead and find Mercury right now. Here's Mercury. And okay, let's see. I got to go find the sun. Let's go ahead and put it in the middle of the sky. Okay, so if you can see right here, I got Mercury. It's 2.8% eliminated. and there's 1.7, 0.9, 0.4, 0.2. Okay, so right around here, looks like right here on 4/11/2024 was our first inferior conjunction. Okay, so now we're at inferior conjunction. The next day, which is this week, right now, and here's today, we are at western elongation because Mercury is to the west of the sun. So everybody remember, what is it then? It rises before the sun. It's called a morning star. Okay. As we go further and further away, watch the elongation numbers right here. The elongation numbers are going to get larger. Elongation is 9.9 degrees, 52 minutes. We're going to go 11, 12. It just keeps getting further and further and further, getting brighter as we go. 23, 24, 25, 26. Okay. And I think, oh, a little bit bigger. Oh, there it goes. Stop getting bigger. So right around there is the greatest Western elongation. And we're going to keep going, right? We want to keep going and we're going to watch it do its cycle. And as it lines up with the sun again, remember, oh, look, Venus disappeared too. And that's going to be our superior conjunction about June 14th. Okay. And then we're going to keep going. It's a full Mercury, by the way. Now it's going in the eastern side. It's going to be an evening star. And we're watching that elongation for the moment that it gets farthest away, 25, 26, 26, right around there is the greatest eastern elongation. And you can see it's getting dimmer now. It's getting dimmer, right? So actually getting not as bright. And here we go. We're getting back to our starting point and 1%. Okay, right around there. So let's see, right around there. So it looks like on 8/18 was the next inferior conjunction, 8/18/2024. We're going to keep going though, and we're going to do it again. Okay, so here we go. Western elongation, greatest Western, greatest Western. And now it's headed back. Superior conjunction, look at the sun is kind of lower in the sky right now. And now it's Eastern elongation. We're going to head over further and further and further away from the sun. And you can see at some point it's going to get the furthest. It'll be great. Oh, there it goes. It wasn't 26 though, a little bit smaller. So something funny about Mercury's orbit, it's highly elliptical rather. So you need to watch it a few times to get a pattern. So we're going to keep going. And now it's coming back to inferior conjunction. Okay, right around there. Right around, it looks like right around there. Right around there. That looks like it's pretty good. 12/5, 2024. Okay, we're going to keep going. All right, so here we go. We're Western elongation. We're waiting for the greatest Western elongation right around there. Ooh, that was pretty fast. Okay. 21, 20, almost 22 degrees. Okay, greatest Western. And now it's getting closer to the sun. And we have, here we go, superior conjunction. And then over here, now we have Eastern elongation. We're looking for the greatest Eastern. Ooh, we already passed that too. Ooh, wow, didn't even get to 20 this time. 18. Okay. So it really changes depending on the orbit that you're watching. And here we go. It came back to about 0.5. Okay. Anything? No, that's it. Okay. About 3/24. Okay. So we got our data. We watched 3 complete cycles of Mercury's inferior conjunction. So here's my data. Okay, here's my data. So we had 1 cycle, 2 cycles, 3 cycles. Now this is 3 cycles, right? 3 times it went through this entire cycle. Now, if you look, okay, we're a couple weeks off. It's about 2 weeks off, but it almost took a year. So because this is a friendly class, I'm going to write this down that 3 times the period, 3 times capital T, is about 1 year or about 12 months. So we're going to go ahead and write that down. So how would you solve for T? And you can see what you do is you divide both sides by 3. And so this is the synodic period. Mercury's orbit, synodic period, because we looked relative to the sun, synodic period. The synodic period is about 4 months. And so 4 months is about how many days? About 120 days. Okay, now we're being friendly here. Okay, remember we're being friendly. So what I want you to do now is we're gonna fill in this table here. We're gonna fill in this chart. We got a synodic period of about 4 months. Okay, 4 months or about 120 days. Okay, so how many degrees did Mercury move during the synodic period? Wow, I don't know. Let's figure this out. So you guys are going to have to understand something interesting that when we watched Mercury, we went from inferior conjunction to the next inferior conjunction. So what I'm going to do is I'm going to show you Mercury's orbit around the sun. We're going to pretend that it's a perfect circle. Here's our sun. And we're going to have the Earth orbit, which is further out, right? And we're going to line them up with each other right here. We're going to line them up. We're going to put Mercury right here, and then the Earth is right here. And so this is inferior conjunction. It's in between the sun and the Earth. It's a new Mercury. Okay. And now, where is the Earth going to be 4 months later? So remember, it takes the Earth 12 months to go once around the sun. So in 4 months, where is it going to be? It's going to be over here, right? And actually, we know something about the Earth. We know that the Earth actually orbits the sun once every year. And we said that it goes about how many degrees per day? Well, it's about 360 degrees divided by 365 days, which is pretty close to what? About 1 degree every day. So in 4 months or 120 days, the Earth is going to move about 120 degrees. Now, 120 is actually a nice number because it's just 1/3 of a complete circle. So there's 120 degrees here, and 120 degrees here, and 120 degrees here, and that makes 360 degrees. There's 3/3 to make a complete orbit. So here's Mercury lined up again, and here it is. It's going to be lined up again. But the idea is that they don't travel at the same speed, right? Mercury is faster than the Earth. It's a race, right? So they take off together. Let's see if I can show you this, right? They take off together, and then Mercury leaves the Earth behind. It goes faster than the Earth. It's going to go around and around. It's actually going to do a complete orbit as the Earth is just doing a fraction of an orbit. And then it's going to come along and it's going to catch the Earth right at this moment. So, in fact, Mercury did one complete orbit and then caught up with the Earth again because it's moving faster. So, how many degrees did Mercury do in that time? Well, it went a full 360, right? Mercury did a 360 degrees to come back to where it started, plus another 120, plus 120, which makes a total of 480 degrees. Let's go ahead and write that in our chart then. How many degrees did Mercury move during the synodic period? It went 480 degrees. So how many degrees per day did Mercury move? So we could do that math right here. We do 480 degrees divided by 120 days. And it turns out the math is pretty easy. And so you do that, you get 4 degrees every day. Compare that to the Earth, which does 1 degree every day. Does that make sense? It's a lot faster, 4 degrees every day, right? 4 degrees every day. So now our final question is, how long would it take Mercury to do one orbit? This is an actual orbit. This is called the synodic or the sidereal period, sidereal period. That's what it's called, right? The time it takes to make one orbit. And the way we're going to do this is remember that when it does a full orbit, it's 360 degrees. So we're going to write it down like this: 4 degrees every day times X days, right? X days, right? However many days it takes, equals 360 degrees when we're finished. So 4 times what equals 360? And the answer is 90 days. Now, This is not, in fact, the right answer, right? That's not quite the right answer. The real answer is 88 days. So that's pretty close. But remember, we were trying to be friendly, and so we didn't get the exact answer. The real answer is, in fact, 88 days. Okay. So that's a little bit of information about synodic and sidereal. Let me go ahead and face the camera here. So that's a little bit about synodic and sidereal. If we look at your Canvas site, we can kind of see a little bit more. Let me just make sure that I've covered everything that I need to cover. You do have a little quiz to take now that you've learned a little bit about this. Let's take a look and see if you've actually covered everything. So we'll get the link to the video in just a second. Inferior planets are closer to the sun than we are. Venus and Mercury are the only ones. They are going to have all the phases, right, from new to full. Superior planets are further from the sun than we are, and they will only be seen at nighttime, which means they're always going to be away from the sun. They're always going to be gibbous or full. And so, yeah, an alignment of the sun, Earth, and a planet or the moon is called a syzygy. So, as syzygy happens every month with the moon, every time you have a new moon and a full moon. So, if it's a planet that's in between the Earth and the sun, we call that a what do we call that? If it's in between the Earth and the Sun, that would be an inferior planet. That we call that an inferior conjunction. If it's on the other side of the Sun, so it's Earth, Sun, planet, then it's called a superior conjunction. If you're talking about the superior planets, they could be, so because they're orbiting further from the sun, they can be on the opposite side of the Earth, and then we would call that opposition. Okay. The normal direction that planets move is towards the east, and that's called prograde motion. When they move westward or in the opposite direction, we call it retrograde motion, and it happens just because the faster planet is passing the slower planet. You can watch that little video clip if you're interested in doing that. Okay, so on Canvas, I will have a quiz that you need to take. And all you need to do is just demonstrate that you learned something from this lecture video. And I think that is it. Thank you so much for your attention. And I hope to see you very soon at the museum.